Hello, rising AP chemistry students. Yes, you guys are juniors now, and now you are the prime focus of my attention, my AP students and the ones who will get my attention this summer. If you're watching this video, it means that you probably have some idea that you intend to take AP chemistry in the fall. One thing I ask you to do all summer is please check your email at least once a week. I will be communicating with you about workshop. I will be communicating with you about what we'll do if we can't do workshop face-to-face. I'll be communicating with you about labs that we're going to do at home if we can't come and see each other face-to-face, and like things like that that are going to go on. It doesn't mean that you're going to be getting work every week. It just means I want to keep in touch with you. In this unit that we're about to start, molecular shapes, there's an at-home lab I'm going to have you do, but I'm going to have to get you some equipment, and so we'll need to be in touch over the next few weeks to get you the materials that you need to do. Okay, so we're going to finish up chapter 8 notes by talking about valence shell electron pair repulsion. So valence shell or electron pair repulsion is the notion that that electrons are repulsive. They repel each other and arrange themselves in a molecule to be as far apart as possible, to be as far apart as possible. So if I have two pairs of electrons, they're going to want to be on opposite sides of that molecule. But if I have three pairs of electrons, they're going to have to spread out too. And how does that mean? And they use three-dimensional space. So there are 5 different ways that these can arrange themselves, 5 different shapes, main shapes that you can get when you're trying to arrange electrons apart from each other. And the first one is linear. And linear looks like this, where there's some atom in the middle, and then it has bond pairs out both sides. And then because they want to be as far apart from each other as possible, they're going to be straight out apart from each other, 180 degrees apart. And this will be something like AX2, where you have a central atom bonded to 2 similar things on opposite sides. An example of this would be BeH2, beryllium hydride, would be in this form. Okay, the next one would be, well, what if instead you had 3 things bonded to the center atom? Well, it's going to make it into a trigonal planar shape. That, which is what this one is, where they're going to want to spread out as far as possible, so they kind of make this triangular shape like this. And the bond angles now are 120 degrees, because it would be like 120, 120, 120, and that makes 360. That's the type AX3. An example of this would be BH3. This would be the shape of boron trihydride. The next one is where it starts to get 3-dimensional. This is a tetrahedral shape, and as you can see, it doesn't lie flat in the plane. So we're going to draw it. We always draw it a little bit like this, where there's the center atom, and then you draw one straight up and one down and to the left, and those are like they're in the plane. So these are in the plane. And then this one is coming at me. So I draw that with a shaded in wedge coming at me, and this one's going away. So I draw that with a dashed wedge going away. That's the convention. And then the bond angle between these is 109.5. It's not 90. It might be, when you look at it, you think, oh, there's 4 things, I'm going to have to split it up. It's going to be 90, but it's not, because they use the 3-dimensional space and they're not all in the same plane. So then that's AX4, or something like methane, CH4, the gas you burn when you turn on the Bunsen burner, is in this shape. And that's an extremely common shape. There's going to be a lot of tetrahedral molecules that we'll look at. The next step up from there is to have trigonal bipyramidal, and I just counted how many of these I needed. 1 second while I grab another hydrogen. Trigonal pyramidal happens when you have 5 electron domains on the center atom. Okay, so now this one has 5 domains, and it's trigonal because they say if you look at it from down the top, there's a triangle in the middle, but then if you looked at it from the side, you could imagine it was a pyramid on top and a pyramid on the bottom. So trigonal bipyramidal. We're going to draw it like this, where we go straight down with the middle one with one above, one below, and one straight out to the left in the middle. And then you have one that's coming towards you on the right and one that's going away on the right. And this has two different sets of bond angles. This angle here is a right angle, so there are 90-degree angles in here, but this angle between these two trigonal ones is 120, so it has both bond angles in it, and that'll be something with 5 things bonded to it, and that would be something like PCl5 would fall into that category. Okay, and the final one, octahedral, has 6 bonding pairs, 6 electron domains on the center atom. So we draw it with one up, one down, and then on both sides we've got one coming out towards us and one going away. And those are all 90-degree angles, AX6, and this is like sulfur hexafluoride. Okay. And if we were doing this in school, up on the whiteboard during the whole week and a half that we would be doing this, is usually the last 2 weeks of school, I would put on the whiteboard a diagram that is kind of a summary of the next 5 pages of notes. And so you should grab a sheet of paper, a blank sheet of paper that you're going to essentially make into your whiteboard, and we're going to add it to it as we go along. So this thing that we just did, these are the possible electron pair geometries. And we'll abbreviate that EPG, electron pair geometry. And so if you have 2 domains, number of electrons, domains around it, if you have 2, then your EPG is linear. If you have 3 electron domains, then your EPG is trigonal planar. If you have 4 electron domains, your EPG is tetrahedral. If you have 5 electron domains, your EPG is trigonal bipyramidal. And if you have 6 electron domains, your EPG is octahedral. What does an electron domain mean? An electron domain means a place where there are electrons. So in a Lewis structure, an electron domain would be a place where there is a pair of dots, a place where there is a line, or a place where there are multiple lines. So if you have a double bond would only count as 1 electron domain. So let's see if we can figure out what the EPG is for silicon tetrachloride here, SiCl4. So we're going to draw our Si in the middle. It has 4 valence electrons. The chlorines each have 7. So 7 times 4, 28, plus 4 more is 32. That's a common one we've seen a lot of times before, where you just get the 4 guys around the center and each of them have their lone pairs around it. Now this has 4 domains. 4 domains, because you're only talking about the center atom, and on the center atom there are 4 different locations where electrons are. On the center atom there are 4 different locations where electrons are, 4 domains. So looking at our chart, 4 domains, this molecule is tetrahedral. And it would be shaped like this. Okay, turn the page 20. What is the shape of dichloromethane, CH2Cl2? Predict the CCl-C bond angle. So we would put C in the middle with an H and an H and a Cl and a Cl. And we bond it like that, and you get dots here, 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 and here. Okay, on that center atom, there are 4 electron domains. 4 electron domains. So therefore, it is tetrahedral. And so the bond angle is 109.5. And we bring this up because if you look at this, it looks like there is a 90-degree angle between these two and a 180-degree angle between these two, but that's false. It is shaped like this, where every bond angle is 109.5 away from every other bond angle on this molecule. So no matter what, no matter where you put those 2 Cls, they're 109.5 degrees apart from each other.